to the third talk, Probabilistic Forecasting of Household Loads, Effects of Distributed Energy Technologies on Forecast Quality. And the presenter is Frederik from Scheidt. And Frederik, if you want to get your slides up, I will introduce you as you do that. So Frederik from Scheidt believes that novel AI applications are a powerful tool for creating a more sustainable energy system. Therefore, as part of his PhD research at the Karlsruhe Institute of Technology, he develops new forecasting applications and appropriate economic mechanisms that, in combination, efficiently integrate decentralized technologies into the energy system. Frederik has repeatedly cooperated with scholars from MIT in the US and INESTEC in Portugal, and holds an MSc in Industrial Engineering and Management from KIT. So over to you, Frederik.
Yes, thanks very much for the introduction. I'm Frederik. Well, I don't have to introduce myself now anymore. Yeah, I'm happy to say that at least I will cover some aspects of electric heating in this talk, and maybe this will be a good addition to the one that Dominic just gave. So let's dive right in. We can see that a number of distributed energy technologies, such as solar on the rooftops, electric heating, electric mobility, or electricity storage, is really disrupting conventional load profiles right now. I guess this is why many of us are doing the research that we are doing. And so we see new net load profiles with an increased volatility, like you can see here on the right side. So this makes it more challenging to have accurate forecasts. And at the same time, though, we have a rising need for good forecasts, for example, for such smart home energy management systems, as we just presented, or also for grid operators. So therefore, the importance of short-term forecasting is rising, and especially for probabilistic forecasting, because probabilistic forecasting has the nice feature that it gives us a bit more information about the uncertainty of future values, of future observations, and therefore it can give us more information, for example, for the operation of management systems. So when we look at the literature of probabilistic forecasting on the individual household level, we can see that it's a fairly young field, and there's really a number of very exciting methods that has been proposed lately. So what is a prevailing gap, however, is that all of these methods have been applied to, let's say, standard household data sets. So with that, I mean households that do not have any exciting technologies, such as solar or electric heating or electric mobility. There's one exception. There are two studies by Van der Meer et al. That look at households with solar on the rooftops, but they again disregard standard households, so they don't give us any insights into how forecasts might be needed to be tuned differently for different kinds of household technology setups, so to speak. So this is the gap that we are addressing with our paper that I'm presenting here. We want to make some probabilistic forecasts for households with different types of energy technologies and see how what kind of insights we can get from that. So we want to give these first fundamental insights in such forecasts. We do that by constructing a new data set that contains net load profiles of 40 households and is differentiated by the heating type, so whether there is electric heating or non-electric heating, and also whether there is rooftop solar or not. We also published this data set with our paper. And then we apply a new method to this data set, which makes probabilistic forecasts based on quantile gated recurrent unit networks. We use weather forecast data and calendar variables as external features to feed into that model. Also check it against 3 benchmark models, and also publish the code for these models with our paper. So let's have a look at the methodology, the structure of our overall model. Here on the left side, you can see basically the setup. We have 3 different kinds of inputs. On the left side, the first input is just historical lag data. So we use the last 2 weeks in 1-hour steps for input data, feed these data through 2 layers of GRU units, and then 1 dense layer, and derive a hidden state in the end, which is meant to capture the kind of the shape of the load curve. And then we have 2 additional external variables that we put in, so calendar information, which is 1-hot encoded, and weather information. Namely, here we use wind speed forecasts, air temperature forecasts, and relative humidity forecasts. So these data are normalized and then concatenated with the other two inputs, fed through two additional dense layers, and then they output not just one point forecast. I think that's really the special thing about probabilistic forecasting, but instead we output actually 5 values for 5 different quantiles, and that's what you can see in the graphic on the right side. So the points are classic point forecasts, and a quantile forecast in this case gives us a bit more information about the uncertainty. You can see wider intervals means that we are less certain about where the actual observation will be. So we measure the performance of these models, of this model by the pinball loss, which is an established evaluation metric for probabilistic load forecasts. And the core idea of this is really to just asymmetrically penalize errors. So if I make my 90% forecast and the actual observation is actually even higher than that, then that should be penalized a bit more, because I was, this is a 90% forecast, so I should be pretty sure. And what is important to note is that the objective of our training process for all the models is to minimize the average pinball loss of all these 5 quantiles. So these are summed up, and then the loss is the resulting losses to be minimized. I mentioned some benchmarks. So we have an according LSTM model. I call this the quantile LSTM model, QLSTM in short, which has basically the same structure as the QGRU model I just showed, just it uses LSTM layers instead of the GRU layers, and also takes the same input features as the QGRU. Then we have a quantile regression neural network model. So here we don't use any recurrent layers, just 4 dense layers, straightforward, fully connected neural network layers, and also take the same input features. And then as the third benchmark, we take a quantile LSTM model, which we basically take from the literature from a recent publication by Wang et al. So this basically corresponds to our QLSTM model, but does not take any weather features as inputs. So we also use that as a benchmark to kind of compare our results to the literature and make this connection here. So we do some hyperparameter tuning. I think what's important to note is that we set up and train a model for each household individually. And we also train the hyperparameters individually for each model. Namely, we look at the learning rates, the number of units in the recurrent layers, and the number of units in dense layers. Of course, there's always a limitation to the hyperparameter tuning. You could, in future work, also look at, for example, the size of the input window of the lag data. That could be something that one could tune, or the number of the layers that could also be tuned. And then we do a cross-validation, and due to the time series nature of our data, we do a expanding window approach, which means that in the first run, we basically use only 80% of the data, and in the second one, we use 100% of the data, and then we average the losses across the 2 test sets to get our final performance. So let's have a look at the data that we use for our case study. We use some data from Chicago in the US and randomly sample households from a larger data set here. It contains the data for 1 year in 30-minute intervals. And what is important is that it gives us information about the housing type. So we can select only the households that are single-family homes, because those are more likely and more valid to actually install a solar roof on the rooftops. And the second information we get from this data set is that is the type of space heating that the households are using. So we know whether they are using electric heating or non-electric heating. And the data set doesn't contain any information about solar installations, or it doesn't contain any households that have solar, actually. That's more accurate. So therefore, we have to simulate it. And this is why I'm speaking of a semi-synthetic data set here, because we simulate the power generation from rooftop solar systems with a Python tool called pvlib. And what's interesting here, I think, is that we simulate 3 different azimuths, so basically 3 different angles. So we have some variation in the resulting solar generation profiles, and then we randomly assign these generation profiles to the households in our data set and subtract the generation from the original load, and that gives us the net load that we then use for forecasting. So here you can see the final data set, the resulting net loads across these 4 types of customer groups. So basically one line in the figures corresponds to one household, and it's the average consumption over the year. And so for the households with no technology, we see a rather steady consumption with a slight peak in the evening hours, as one would expect. For the households with electric heating, we see these characteristics peaks, especially in the morning hours when presumably the heaters are running and consuming electricity. For the households with solar, we see this characteristic dip around noon with the duck curve. And then for the combined data, we see both the peaks and the dips. And actually also, I think what's interesting is that we have a negative net load here with the solar. So to sum up, what we use as input variables is the hourly net load of the last 2 weeks, then the calendar variables, weekday and time of day, and 3 different weather variables. And that is fed into the model, and then 1 hour ahead forecasts are put out. So let's have a look at the results. What we find, first of all, is that the proposed QGRU achieves the lowest average pinball loss across all the different customer types. And it outperforms the benchmark models in roughly 2/3 of cases, which is also what you can see on the right in this graphic. So here we are plotting on the y-axis the QGRU loss, and on the x-axis the loss of the benchmark methods. And that means that all the points that are below this diagonal are actually cases in which the QGRU outperforms another model. And especially it outperforms most often the QRegNN and the QLCM without the weather data. But now let's look also a bit deeper into the results differentiated by customer groups. So here we can see, first of all, that for the standard households, so the standard households that have no distributed energy technologies, actually the QLSTM without weather data, which we took from the literature, is the one that achieves the lowest loss. I think that's quite interesting. And it also confirms that this is a well-performing model. This is what you can see in the table. But this doesn't hold true for, sorry, now my mouse is not working anymore. Okay, here we go. But this is not true for the households with technologies. So for all these 3 types of customers with distributed energy technologies, actually the QGRU achieves the lowest loss. So this is already interesting because it kind of, lets us assume that we need to maybe tailor models specifically to the households if we know what kind of technologies they have. What we also find here is that for all models, the highest average loss always occurs for the households with electric heating, and the lowest losses occur for households with solar generation. So if we look a bit deeper into that and try to find out why that is, we find that, so here on the right, you can see the graphics where we plotted on the x-axis the annual net consumption of households, and on the y-axis the loss, and that for the 4 different models. So what you can see is there's always one blue dot at the right upper side, which represents one customer, which seems to be particularly difficult to forecast. So this lets us assume that maybe a training set of less than 1 year, so we use 1 year in total as a data set. So maybe this is not sufficient to actually for the GRUs layers to learn about heating behavior, or for the model as a total to learn how heating impacts the electricity demand. What we also can see is that we have low losses for the households that have solar installed. These are the triangles on the far left side in the graphics. So here it seems to suggest that the models can adequately capture the periodicity of solar generation. And what is furthermore interesting, I think, is that for the households that have both solar and heating, so these are the bright blue, the dark blue ones here in the middle, kind of with the medium consumption, they have lower losses than their corresponding households with no technologies, even though the net consumption on an annual level is roughly the same. So this kind of seems to suggest that maybe this periodicity in the solar generation, which can be forecasted quite nicely, maybe more than outweighs the kind of difficulty that electric heating brings into the net load profiles. And we see that within each group, the total annual net load and the loss. So therefore, we can also say that doesn't seem to be too characteristic for the net load loss. And we also looked into the of them, but that also doesn't lead to higher forecast errors. So to conclude, we are providing a quantile GRU model which can make forecasts, probabilistic forecasts for residential net loads. We construct a new semi-synthetic net load data set, and we publish this. As I mentioned, if you're interested in using this, maybe as a benchmark data set in the future, you can find the link in our paper, and also the code, as I mentioned. If you want to have a look at the code, maybe use it for some other endeavors, you can have a look at that. First important finding is the best model for households without any technologies is the quantile LSTM from literature, and this doesn't hold true for the other households. So as soon as we add solar or electric heating to our load curves, then actually a different model performs best, the proposed QGRU. Forecasting losses lowest for households with solar installations and highest for households with electric heating. And that lets us conclude that increasing adoption of these technologies is likely to affect the quality of existing forecasting tools. So I hope we were able to provide some insights for these probabilistic forecasts on household loads with different technologies. And I'm very happy to take any questions or comments. Thank you.
Great. Thank you very much, Frederik. Yeah, great talk. We do have a couple of questions lined up already, so I'll go straight to the ones in Slack. Jonas, you had the first one.
Yeah, so Frederik, can anyone hear me? Everything's okay?
Yep.
Yes.
Super. Had to switch to a backup internet connection. So again, great presentation. I wanted to ask about the semi-simulated data. Have you used any sort of validation method to make sure that the data is sort of makes sense and in line with what you would expect?
So if you're referring to the solar data, yes. So we are using basically a tool that has, is very well documented. I link it here. We also linked to it in the paper. So there's a whole paper about this PVlib tool in Python. And it basically uses real external weather data, so irradiation, for example, temperature, and so on. And the exact coordinates of where you are to generate these load profiles. So I think it is fairly valid, but I don't know the documentation by heart, so I would have to have a look at that again.
Understood. Well, I think that makes a lot of sense. They probably developed it pretty well. Another question would be about probabilistic models. So here we're using sort of quantile predictions to output a probabilistic forecast. Have you attempted to compare like a typical point-to-point network's performance to a probabilistic model's performance? Because recent research sometimes shows some pretty huge disparities in performance. The fact that you add probabilistic outputs actually degrades the performance quite significantly in some cases.
Oh, really? No, that sounds interesting. No, we have not benchmarked against a non-probabilistic model. I think that would be interesting. Yeah, I think in general, like adding more benchmarks is always interesting. You can always be surprised. So if you have a certain paper in mind that shows this effect, I would be very interested in having a look at that. Yeah.
I'll link it after my presentation.
Cool. Thanks.
Great. Thanks, Jonas. There was also a question from Niels. Niels, do you want to ask it?
Yeah, thanks. Can you hear me?
Yes.
Cool. Yeah, so I was just wondering with these quantum networks, how long do they take to train, like compared to normal point regression networks? Is there a huge difference?
It takes longer. Yes, it takes longer. it's always difficult because it kind of depends on, you know, what kind of computer you use, what setup, and how well you can parallelize maybe computations. And since I didn't calculate a point forecast benchmark, I can't really say, but it takes notably longer. That's what I can say. Yes, it's more computationally intensive. So that's a disadvantage.
Okay, cool. And then did you, how did you validate the quantiles you predict afterwards? Is that just in general, like 90% of the time we're inside the 90% highest density interval? Or how do you do it?
Yeah, this is basically what the model tries to learn. So to make a, to basically make an estimate for a future probability. It estimates what kind of probability a value will be below a certain value. And that's what it tries to learn.
But it's the pinball score in the end, isn't it? That you're using?
Yeah,
to
that's what we're using. And so what I think is also notable that we are minimizing the total pinball score across these quantiles. So what one could also do, if you have more powerful computers and more time, you could actually of course you can have more quantiles. You can have like 100 quantiles if you want to have like 1% per quantile. And then you can also, of course, minimize the loss for each quantile individually. But that takes, again, a lot more time.
Okay, cool. Thanks.
All right. Okay. Well, thanks again. Thanks very much, Frederik.
Sure. Thanks.
And since we're on time, I think we'll move on to the next talk. And any other questions, please post them in the Slack.